All right, welcome back, Senior Math. Today we are going to continue talking about hypothesis tests. This is going to be our last type of hypothesis test that we will talk about this week, I believe. Um, this should be the last one. I don't think there's any other ones, unless I'm drawing a random blank. All right, so we recently learned how to change our hypothesis test for when we have two means that we needed to compare. So we had two different population means. We were testing whether the difference of the populations was accurate or not, or the mean of that population was what it claimed. We were testing those hypotheses. Now, today, we will look at how we can adapt our hypothesis test for when we have data from a binomial population. So let's review what that word binomial means, because we talked about binomial distribution earlier this year. So binomial distribution is an experiment where the result has only one of two different outcomes, can only have one of two different outcomes. For example, if you flip a coin, it's either going to land on heads or it's going to land on tails. You either have blonde hair or you don't have blonde hair. You're wearing a red shirt or you're not wearing a red shirt right now. So it's either you meet the requirement or you don't meet the requirement. So that's a binomial population. So we're going to talk about how we can change this hypothesis test to allow for binomial situations using percentages or using proportions. So that's what we're going to look at. So when we're looking for a binomial population, we need to figure out what is the proportion, the percentage of the population that has the desired result that we are looking for. So we are always looking for the specific proportion. So what percentage of that population has that desired result? What percentage of that population has blonde hair? What percentage of that population is wearing shorts or wearing a red shirt? I don't know. Whatever the question is. So this proportion is represented by the variable p hat. So this little p that has this little line, like a little arrow at the top of it, it's called p hat, like you're wearing a hat on the top of your head. So to calculate p hat, we use the formula p hat equals x divided by n, where x is the number of people with the desired result. So if you're asking a bunch of people, or if you're like surveying a bunch of people whether they have blonde hair, however many people have blonde hair is going to be X. N is the total number of people, the sample size. So if you survey 500 people for blonde hair and 38 of them have blonde hair, you would have 38 out of 500 would be your p hat. And so whatever that percentage is would be our, or whatever that decimal would be our binomial or our proportion that we need. So that's how we calculate the proportion. So just like with all of our other hypothesis tests, we have to look at what is the type of test. So we have our left-tailed test, our right-tailed test, our two-tailed test. The same test that we've been doing all these times. We're going to use those same percentages, that 5%, the 5%, the negative 1.96, the positive 1.96, the negative 1.64, and the positive 1.64, depending on whether you're a left, right-tailed, or two-tailed test. But we need to state what is the null hypothesis and the alternative hypothesis, just like our always test. Now, the awesome thing about binomial experiments is the null hypothesis is always going to be the same. The null hypothesis is that the proportion is equal to what the claimed proportion is. So there is always, with these questions, there's always going to be a claim. Someone is claiming that this percentage of the population has this trait, or this percentage of the population does this thing, or this percentage of the population XYZ. So the claimed proportion is this P null or P0. So the null hypothesis is always going to be that P hat is equal to P0. And that's for any type of test. Now, depending on whether you're doing a left-tailed test, a right-tailed test, or a two-tailed test, would determine whether you're showing that the alternative hypothesis is that the proportion is less than what is claimed, the proportion is greater than what is claimed, or the proportion is just different than what is claimed. So those are our different types of tests. So it's nice that the null hypothesis is always going to be P hat equals P sub 0. It just depends on whether you're showing that it's less than. So less than, greater than, or just showing that there is a difference between the two proportions, that there's a difference in the claim. And now, because we're changing our proportion we're changing, we have to change our z-score for our binomial test. Let me move this down here. All right, so the z-score formula for a binomial hypothesis will also be needed to change slightly. So z is going to be equal to p hat. Once again, p hat we can calculate by doing our result of number of people with the desired outcome divided by our sample total. So we get p hat minus the claimed proportion, p sub 0, the original proportion that is stated, divided by the square root of p sub 0, once again, that's the claimed proportion, times q sub 0. Now, q sub 0 is essentially the proportion without the desired result. So if they're claiming that 25% of the population has blonde hair, that means 75% of the population, the other proportion, the other part of the population, does not have blonde hair. So p sub 0 would be 25. 75% would be the q sub 0. And one way to always do this is just do 1 minus that decimal. So q sub 0 is always going to be 1 minus p sub 0, the proportion without the desired result. So if it's always out of 100%. If you think 45% has this result, that means 55% has the other result. And then once again, n is always going to be the sample size. So we're going to do p hat, the x minus n, the population with the desired result divided by the total population, minus the original claimed proportion, divided by the square root of your claimed proportion times your claimed proportion without the desired result, divided by n, your sample size. And that's going to give us our z. Then once again, just like normal, we're going to do those 5 same tests. So write the null and alternative hypothesis that we talked about. Determine what type of test we have that we're performing, whether it's a left-tailed test, a right-tailed test, or a two-tailed test. Locate the critical regions. Remember, if it's a left-tailed test, left critical region is equal to negative 1.64. Right-tailed test is positive 1.64. And then a two-tailed test is always going to be either less than negative 1.96 or greater than positive 1.96. So those are our critical regions that we're always looking for. We'll calculate the z-score using our formula that we just talked about, and then we'll determine whether to keep or reject that null hypothesis, whether their claim is true or whether their claim is false, whether there's enough evidence to discredit their claim or whether there's enough evidence to support the claim. All right, let's look at some examples. So, example 1, regardless of age, about 20% of American adults participate in fitness activities at least twice a week. So I already see I have 20% of American adults participate in fitness activities twice a week. However, these fitness activities can change as people get older, and occasionally participants become non-participants as they age. In a local survey, N equals 100 adults, so that's my sample size of adults, over the age of 40. A total of 15 people indicated that they participated in fitness activities at least twice a week. Does this data indicate that the participation rate for adults is significantly less than 20%? So let's start with our null hypothesis. So we know the null hypothesis is always going to be the h sub 0 is that p hat is equal to p sub 0. So the null hypothesis is that p hat equals p sub 0. So that means my alternative hypothesis, I'm trying to see, is there enough evidence to show that this is less than 20%? So p sub 0 I know is 20%. That is the claimed amount. I should put that. So 0.20 is 20% as a decimal. So I'm trying to show, is p hat less than 0.20? Is it less than 20%? So if I think about my critical regions, if I think about my curve, 20% is the bottom, or if I'm doing less than, I'm doing less than 20%. My critical region then, because I'm less than, is negative 1.64. I need to get a number. If I get a number that's less than negative 1.64, then I know that I have met my critical region. So let's test our z-score. We know z is equal to p hat minus p sub 0 divided by the square root 0 times q sub 0, all divided by n. So let's start filling in this information. Well, p hat is equal to my desired result divided by my total number of outcomes. Well, I know that 15 people had the desired result, that they participated in the fitness activity at least twice a week out of 100 people. So if I do p hat is equal to 15 divided by 100, that gives me 0.15. So this is going to be equal to 0.15 minus my p sub 0, which I know is already my 20%, my 0.20, divided by my square root of p sub 0, once again, which is 0.20, times q sub 0. Now, q sub 0, once again, is the percentage that does not have the outcome. So if 20% does have the desired result, then the amount that doesn't have the desired result is 80%, so 0.80. All divided by my n, which is 100. And I can plug this straight into the calculator. So I'm just going to plug this whole thing right here into the calculator. And then that's going to give me my z-score, so just like we've done before. So my z-score is from that negative 1.25. Is that right? Yeah, negative 1.25. So negative 1.25 is my z-score. If I look, negative 1.25 does not quite reach my critical region of negative 1.64. So because I do not reach my critical region, there's not enough evidence to indicate that this is incorrect. So I am going to keep my null hypothesis. So there's not enough evidence to indicate this is incorrect. So this data does indicate that the participation rate for adults is over 40, is significantly not less than 20%. There is not enough evidence to say that it is less than 20%. So we're keeping that null hypothesis, and we are done. So that is how we calculate binomial hypothesis tests. Let's do one more example. All right. According to the American Obesity Association, the number of overweight children and teens is at least 15%. Suppose that you survey 750 children and teens, and the number considered overweight is 68. Does this data provide significant evidence to assume that the proportion of overweight children and teens is different from the reported proportion by the American Obesity Association? So once again, we're starting with our null hypothesis. So my null hypothesis is that p hat is equal to my claimed percentage, which is 15%, so 0.15. I'm trying to see if this data indicates that there is a difference between this reported amount. So I'm just trying to show that the p hat is just different than 0.15, that my data is different than 0.15. So if we're trying to show this is different, this is going to be a two-tailed test. Let's talk about our critical regions. So our critical regions, we can either be below that value or greater than that value. But because it's a two-tailed test, I need to use smaller numbers. I'm using negative 1.96, so I can be 95% confidence, and positive 1.96 and negative 1.96. I put my negative on the wrong side. So I need to see if I get a number that's less than negative 0.196 and greater than positive 1.96, then I know I have 95% confidence that there is significant difference between this. But if I don't get within that range, then there's not enough evidence to support this claim. So let's see what our z-score is then. So we know, once again, z is equal to p hat minus p sub 0 divided by the square root of p sub 0 times q sub 0 divided by n. And let's start filling in our information. So p hat, I need to figure out what p hat is first. So I have to look at my data. I have 68 children and teens are considered overweight out of my 750. So let's find p sub hat. So p hat said that it was 68 out of 750. What is that, decimal? Well, 68 out of 750 should give me a decimal of 0.09. So I have 0.09 minus p sub 0, which p sub 0 was 0.15. So divided by the square root of p sub 0, which is 0.15, times q sub 0. So once again, q sub 0 is just 1 minus my decimal. So 1 minus 0.15 is 0.85. So 85% does not have that desired result, divided by n, which is 750. Plugging all of this information into the calculator, we get a z-score of negative 4.6. So this is very, very low, negative 4.6. It's way off of our map, way off of our normal curve. And so because that z-score is way lower than negative 1.96, we have plenty of evidence to say that we are going to reject. We are 95% confidence that we can reject our null hypothesis, and that this claim right here, the American Obesity Association, that this number is definitely different than 15%. Our data did not come out to be the same result. And so that is how we do our binomial hypothesis test. So it's pretty much same strategies. Once again, same 5 steps that we've been doing all last week. The only difference is this little formula is a little bit different. We have to work with some percentages, and we need to use that p hat value. But everything else is still going to be the same. Our whole strategy is still the same. It's just how you set up the formula and what formula you use is the only thing different. So that's where we'll end it for today. Let me know if you have any questions. You'll have a little bit of practice of this, and then you'll do your own tests with the class data about whether or not our data matches the American Veterinary Medical Association's claim about the number of households that have cats. Have a great day.